Well, hello ladies and gentlemen, Mr. G here to talk about our final lesson in our unit on permutations and combinations. And today we're going to take a look at this neat mathematical tool that a lot of people don't realize how powerful it is, and that's this idea of the Pascal's triangle. And we're going to connect Pascal's triangle to these combination questions that we've been dealing with over the past couple lessons. After that, we're going to talk about the binomial theorem. And again, how combinations can be a very useful tool in the idea of expanding ridiculous binomial multiplications out. So, first thing I'll mention is this idea that, as usual, this is an investigation type lesson, meaning that you should be able to work through these questions on your own without my instructions. So I encourage you, please take a look at these questions before I start talking about them and see if you can't come up with some conclusions yourself. It's going to go a long way in helping you down the road. Okay, so first question here says that Marion has invited 6 friends to a barbecue at her home. She did not ask for a response to her invitation, so she is not sure how many people are coming. How many combinations of guests could actually occur? This is the type of question that you dealt with in the previous lesson, and that's the idea that we have to deal with different cases. So the cases in this case are, well, if 0 friends show up, well, we had 6 possibilities, and we're going to choose none of them, which means that there's only one combination in this case. We have 1 friend shows up, good friend. 6 choose 1 means that there's 6 possibilities in this case. If we move down the line now, 2 friends, 6 choose 2. I think we're starting to see a pattern now. And 3 friends is 6 choose 3. Keep in mind that these are just dashes, not minus signs. Tell you what, make them arrows just to make everybody happy. And 6 choose 3 is 20. 4 friends show up. Well, possible combinations is 6 choose 4, which is equal to 15. Again, interesting that it's now going backwards. 5 friends, 6 choose 5, which is equal to 6. And finally, if all 6 friends show up like good friends, 6 choose 6, which is just equal to 1 way of dealing with it. So the total number of combinations then is just, as we found out previously, the sum of all of these numbers. So 1 plus 6 plus 15 plus 20 plus 15 plus 6 plus 1, and that is just equal to 64. Now, I wrote this in a particular way, and I want you to take note of a certain pattern that I hope you see in these numbers. First pattern you might notice is that we have a beautiful symmetry going on here, where you have a 1 on either end, then you have 6s right after, then you have 15s, and then you have this beautiful 20 in the middle. It's symmetric on either side. That is an interesting sort of situation there. So I want you to think about this particular sequence of numbers here, because we're going to go down now and remind ourselves of what the Pascal's triangle is. Now, if this is your first time seeing the Pascal's triangle, good for you. This is an exciting thing. If this is something that's not new to you, also good for you. You should have known it anyways. So, Pascal's triangle is a triangular set of numbers that work like this. We end up with 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Are you seeing symmetry in this triangle as we go down? 5, 10, 10, 5, 1. And I'll just do one more row because this might raise some red flags to you. 20, 15, 6, and 1. So this is the first few rows of Pascal's triangle. Now, Pascal's triangle works like this. When we're dealing with rows, the very top row Well, that's actually row 0. So row 0 is just that 1, 1 at the top. And then we go row 1, row 2, and we label this one down here row 6. If we take a look at this sequence of numbers and we compare it to our original, well, isn't that cool? It's the same sequence of numbers. So Pascal's triangle relates to the combinations in some way. Let's learn a little more. We dealt with if we're going by rows, but what about each individual term within the row? Well, the standard notation is that this first number here, and I'll leave a space for a reason which will become apparent in a second, is called position 0. Much like our row numbers, we start at 0, which means that that 6 there is going to be position 1. And so on and so forth, all the way to position 6. Okay, so we have position 0, position 1, position 6. Now, let's think back to our first question. How did we end up with this number 1 using combinations? Well, we said that it was 6, choose 0. And if we move along the line, the 6 was 6, choose 1, 6, choose 2, 6, choose 3, 6, choose 4, 6, choose 5, and finally 6, choose 6. Well, all of our combinations now relate to these terms in the Pascal's triangle. Well, let's see if we can relate any of the numbers within our combination notation to things we know in Pascal's triangle. Well, let's start with this 6. Well, this 6 is exactly the same as the row number that it's in. And this 0 is exactly the same as the position number it's in. So take a look. If we called this one position 1, position 2, position 3, well, that's still a 3. This is still a 4, 5. So that works out beautifully. So when we're answering this observation relationship to NCR, N is the row number, and R is just the position number. Isn't that cool? That means if we know any of the for any combination type question, if we know that there's 6 objects that we're going to change the combinations of, we know that we could just go to row 6 in the Pascal's triangle and we'd get all the different numbers for these particular situations. Isn't that wicked? I thought so. So let's move along. Now, there's more to it than just that, and we've pointed this out before with the numbers. There's a symmetry involved. If we take a look at our numbers again, and we'll just scroll up a bit. Take a look. Our number here for 6, choose 0 is exactly the same as 6, choose 6. And it goes along, 6, choose 1 is the same as 6, choose 5. Well, let's try and prove that. If we take a different situation altogether, let's say we want to take 5, choose 1. Okay, so if we go up to the row, 5, choose 1 is 5. That should be equal to 1, 2, 3, 5, choose 4. Okay, well, let's use the actual formula to calculate these combination numbers. Well, this is 5 factorial over 1 factorial times 5 minus 1 factorial. And that's supposed to be equal to 5 factorial over 4 factorial times 5 minus 4 factorial. Remember, we've already defined this equation in a previous lesson. And if we simplify this now, we end up with 5 factorial over 1 factorial 4 factorial is equal to 5 factorial over 4 factorial 1 factorial. Well, that's just the same number. So in conclusion, we can say something in the general case that if we have NCR, well, that's just equal to n, c, n minus r. Take a look at what we had. This is r. This is n minus r. It's just the same thing. So this is a symmetric property of the Pascal's triangle. Like I say, this thing is just powerful. Let's take a look at another pattern, which is going to be awfully useful when we start dealing with these pathway problems again. And it's this idea of the recursive property. If we just write out the first couple of rows of the Pascal's triangle, I'll put this up here. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So that's just the first 4 rows, counting that the first row is row 0. Okay, now, if we take a look at this value right here, okay, when we talk about the recursive property, what we mean is that it is actually the sum of 2 previous terms. So check this out. If we have this term, this is actually equal to that term plus that term. Let's see if this continues. I'll do it in a different color. This term here is equal to that term plus that term. Whoa, there's something going on here. If we start to label these, what we're saying here is that 3 choose 1 is equal to 2 choose 0 plus 2 choose 1. And we also said that 3 choose 2 is equal to 2 choose 1 plus, whoops, 2 choose 2. Okay, so can we write this much like we did before, a generalized equation given this property? Well, if we start with NCR, well, that has to be equal to, well, this here is just n minus 1. C, well, this is just r minus 1 plus, again, n minus 1 c r. It's just the r. Well, there it is, my friends, a generalized equation which basically says that the term in the next row is actually the sum of 2 terms that are directly across or left to right of the term we're trying to find. Well, that's fantastic. Can we use that for something? Oh, you bet we can. Let's go down here to a pathway problem. Now, we've dealt with pathway problems in the past, except this one here, check it out. We have a nice little hole in here. So what are we going to do? Now, previous ways that we dealt with it are that we break it up into different situations and then we multiply all the combinations together or add them up, and that's how we're dealing with it. We can't do that in this case because we've never dealt with a hole before. So what can we do? Well, we've noticed again that combinations are directly related to Pascal's triangle. So let's start labeling this with Pascal's numbers. And again, I want you to think about this as if it were twisted up to look more like this, right? Because this is now just a grid which would represent Pascal's triangle. And if we started putting in the numbers, we know that in row 1 it's 1, 1, and in row 2 it's 1, 2, 1, and in row 3 it's 1, 3, 3, 1. So this is an idea called the techniques of Pascal's triangle, because now what we're seeing is that all of these numbers relate to each other. Well, how do we deal with that? This term right here, and I'll change colors, is a tough one, because do we just pretend that Pascal's triangle extends out and then put the numbers in? No. But what we can do instead is use the recursive property of Pascal's triangle, which says that this term right here should equal that term plus that term. So 3 plus 1, which equals 4. Okay, so if we continue that pattern along, this number right here should be 3 plus 3, which equals 6. All right, and that means this is a 4 here. Do you see how this works now? That's cool, because now this term right here, I'll change colors for fun, is 10. This one right here is also 10. What about this one down here? Well, we have 4, but then it's plus nothing, so it's 4 again. And think about that, because the picture, it totally makes sense. The line just is a straight line coming down, and if we just had to follow that line, once you got to that point, it doesn't matter how far down you go, there was still only 4 ways to get to that intersection point. So that has to be right. Well, let's fill in the rest. And in this case, again, that would make this 10, and that would make this 10 because it's only adding to one number. This number down here would be 20, and this number down here would be 30, and this number down here would be 40. I hope you're picking up on this pattern. If not, go back and take a look at the explanation we gave, and hopefully that will make sense. This is 14. Okay, this is still 4. This is now 18. 32. Well, how do we get 32? Because this here still has to be 14. So 18 plus 14 is 32. And then right here, we have a 44. Because 14 plus 30 is 44, which means this now is 76, 84, and finally 160, which means that how many different paths can A take to get to B, assuming that you can only move right and down? Well, the answer is 160. And all we did was use the recursive properties of Pascal's triangle and start off by labeling off the different rows of Pascal's until we had to break off from that pattern. So that's a really neat and fast way of coming up with our different paths. So if you don't believe me, go back to your path questions and see if you can't come up with the same answer just doing what we did now, which is break it down as if it were Pascal's triangle. Okay? So the history of Pascal's triangle is really cool. I encourage you to go take a look at it. It's actually named different things depending on what country you go to. That's pretty neat. Take a look. Okay? On to the next one. Our final topic of this particular unit is this idea now of the binomial theorem. And to start off the binomial theorem, we have to come up with some patterns. Let's start off with this, expand and simplify. So you've been doing this since about grade 10, so I'm not going to pretend that you don't know how to do this, but I will write some things out just for the sake of finding a pattern. Well, a plus b squared is equal to a plus b times a plus b. Use FOIL or whatever methods you use to expand it out, and you should end up with a squared plus 2ab plus b squared. Everybody in the room and in grade 12 should be able to do that without any difficulty. But what about a plus b cubed? Well, that's a little trickier again because you have to expand the first two binomials out first and then expand it into the third binomial. So again, you've already found out what the answer to this is, and you would just take that and expand it in to the third binomial. It gets ugly, but you should end up with a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay, again, most of you have probably done a couple trinomials in your, or not trinomial, but binomials that were cubed before. But what are we going to do about a plus b to the power of 4? That is hideous, because that's equal to a plus b times a plus b times a plus b. And I'm going to stop repeating myself, but there you go. So what? Well, again, we have the answer to this one from the top, and you would just expand every term through the final binomial, and you would end up with a to the 4 plus 4, a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4. So again, You could do this by hand, and it would take you hours upon hours. But the next question asks you on the other page, what patterns do you see in the powers of A? Well, let's take a look. We have A cubed to start, and then we go down to A squared, and then we go down to A to the power of 1, and then we go down to nothing. So what's happening to our powers of A? Well, let's see if I can get that. It goes down by 1, or decreases by 1. What about the powers of B? I think you're starting to pick up on something here. We go from no b's to b to the 1 squared cubed to the power of 4. So it's actually increasing by 1. Wow, that's insane. Okay, well, here's the aha moment for you. What about the numerical coefficients in the expansion? Well, if we take a look again, back here, we have the number 1, 3, 3, 1. And up a little higher, we have 1, 2, 1. And then we have 1, 4, 6, 4, 1. Lo and behold, if you went back to your first page out of disbelief, you found out that really it's just the rows of Pascal's triangle. So all those years of having to do them by hand, and you had Pascal's triangle all along to deal with. Now, another way, again, we can write this, and we've already found this out, is that's just NCR, where N was the row number and R was the position number. So, given that information, can you expand A plus B to the 5th? Well, let's start by writing out our A's. We said that A started from our top power, so that's A to the 5th, and then it went down. Okay, so A to the 5th, A to the 4th, A cubed, A squared, A, and then nothing. And then what about our B's? Well, we started with nothing, and then we have 1B, 2B's, or B squared, B cubed, B to the 4th, and B 5th. These are all pluses in between. But we're missing one important thing, and that's the numbers, the coefficients, and that we just get from Pascal's triangle. And this is going to be a 1, 5, 10, 10, 5, and then another 1. And remember, this is just 5 choose 0, 5 choose 1, all the way up to 5 choose 5. So there you have it. Instead of having to do it where you expand every binomial out, we simply know the pattern involved with these particular binomials. Well, isn't that exciting? That means you should now be able to do these particular binomials by hand relatively easy. One thing I want to point out is, remember that in all of our examples, we let the first term equal A and the second term equal B. So make sure that no matter which question you're dealing with, that's how you do it. So I'll do the first couple with you, and then I'll just write out the answers for the last couple, and hopefully you will have already seen the pattern and be able to do those easily. So we have x plus 1 to the 4th, or to the power of 4. Well, that's just equal to then 4 choose 0 times x to the 4 times 1 to the 0. Remember, this is now b, right? And then we add 4 choose 1 x cubed. So remember, our a powers are going down, and now our b powers are going up. And keep going. 4 choose 2 x squared 1 squared plus 4 choose 3 x times 1 cubed plus 4 choose 4, and that's x to the 0, 1 to the 4, but remember that's just equal to 1. So we end up with, well, what do our coefficients say? 4 choose 0 is just 1, x to the 4, obviously 1 to the 0s is 1, plus 4 choose 1 is 4, x cubed, that's still just a 1, plus 6, x squared, still just a 1, plus 4x, just a 1, plus 1 because x to the 0 is 1. So there we go again. Yes, you don't have to include this 1 up front, but I do anyway, so you know where it comes from. So that's just equal to that. Big box around it, happy face. So all we did was use our combinations, have our powers of our A term decreasing, have our powers of B term increasing, and you end up with the correct solution. Well, what about B then? Because B is very much the same thing, except now we're starting in row 6. I'm just going to write this out for you. And you end up with an answer of x to the 6 minus 18x to the 5 plus 135x to the 4 minus 540x cubed plus, wow, that's supposed to be 540x cubed plus 1215x squared minus 1458x plus 729. Now, I'm sure some of you are panicking and going, wait a second, those coefficients have nothing to do with Pascal's triangle. Well, that's absolutely correct. But keep in mind now that we have this minus 3. So when we actually start to fill out the equation like we did before, we're going to have 6 choose 0, x to the 6, negative 3 to the 0. So that's still going to be a 1, and this is going to be a 1. But look at our next one, plus 6 choose 1, x to the 5, because it's going down in powers. But then we have negative 3 to the power of 1. So now we actually have this multiplicative factor that gets multiplied to our coefficients from Pascal's triangle to actually end up with these big numbers up here. So keeping on, your last term would still be 6 choose 6, x to the 0 times negative 3 to the 6. Does that make sense? So we're just using this for this equation, and we're plugging in the values, and away we go. Let's show you how to do C again, and then you can do D on your own. So again, this is A, and that is B. This is our row number. So we start off by saying that we have 4 choose 0 times 2x to the power of 4 times negative y to the power of 0. Well, perfect. Let's move on. Plus 4 choose 1, 2x power of 3, negative y to the power of 1, plus 4 choose 2, 2x squared, negative y squared, plus 4 choose 3 times 2x times negative y cubed, and finally plus 4 choose 4, 2x to the 0, negative y to the 4. So big thing to watch out for here is your negative signs, because you're going to be squaring and cubing stuff, so you're going to get some negative signs some places, and others you're not going to get any. So after you simplify all this out, I'm going to assume that you can take 2x to the power of 4 and get 16x to the power of 4. So we should end up with 16x to the power of 4 minus 32x cubed y plus 24x squared y squared minus 8xy cubed plus y to the 4. You know you've done it right if you watch your powers decrease on your x and increase on your y. Okay, so doing the exact same thing with part D, you should end up with 243x to the power of 5 plus 810x to the power of 4y plus 1080x cubed y squared plus 720x squared y cubed plus 240 xy to the power of 4 plus 32y to the 5th. So again, exact same equation. You're starting in row 5. You should have no problem dealing with this. But let's go ahead and establish the official equation, which is already written for you. And that's this idea here, the binomial theorem. For those of you going into engineering or business, you're going to find out you're going to use this a lot more than you thought. And here it is. So we have all of our different distinctions. First term, k plus 1 term, n plus 1 term. Please keep in mind that these ideas are just because both of them start at 0, so we have to include that plus 1 to show the nth term, right? Now, there is a really useful equation here, and that's that idea of what if you want to find a particular term? This idea of t sub k plus 1 is equal to n choose k, a to the n minus k, b to the k. Whoops. What this thing does is it tells you what any individual term within your expansion actually is. Let's give you an example of what I mean by that. So let's use this in an example now. Example 2 says, determine the fourth term in the expansion 2x plus 5 is equal to 9. Remember that a is equal to this and b is equal to that, and we're dealing with n equal to 9. The problem is, how do we use this for? Well, it says for this expansion the k plus 1th term is equal to our new equation, which means that k plus 1 has to equal 4, which gives us a k equal to 3. Well, that's fantastic. That means we can now use the equation t to the 3 plus 1 is equal to, well, we're dealing in the 9th row, and k is equal to 3 times our a value, which is 2x to the power of 9 minus 3 times 5, which is our b term, to the power of 3. Well, that's supposed to be a 1, which means our fourth term is just equal to 672,000 x to the 6th. So you could imagine actually trying to count that because you'd have to know Pascal's triangle to 9 rows and all these different ideas. Now we can actually just exploit this equation and come up with an answer to a ridiculous question quite easily. Isn't that cool again? So the exact same thing happens for the next couple of questions. You need to find what your k value is. You need to find what your a and b's are, and away you go. So I'm just going to give you the answers to these, and you just need to employ the equation correctly. Our t for the 7th term in this expansion is equal to 20,412 xy to the 6th. Example 4 now just goes back to using the binomial theorem correctly, where again this is equal to a and this is equal to b, and you simply just need to calculate the first 4 terms using the binomial theorem. So in our case we would end up with x to the power of 12 plus 24 x to the 11y plus 264 x to the 10 y squared plus 1760 x to the 9, y to the power 3. So if we take a look at example 5, now we're trying to find, in the expansion of x cubed minus 2 over x squared to the power of 10, find the term containing x to the power of 5. That's a bit trickier because now we're looking for a specific power to our variable x. Now, there is a brute force way of doing this, and then there's a more intuitive way of doing this. I'm going to show you both. With the brute force way of doing this, you simply need to calculate what each of the terms is. So term 1 is equal to what? Well, this is A, that's B, 10 is M. In our case, to find the first term, K has to be equal to 0, which means we have 10 choose 0, x cubed to the power of 10, negative 2 over x squared to the power of 0, which is just equal, after all the expansion, 10 to the power of 30. So, it's not there. Well, let's try term 2. Well, that's the same thing. We put in all our numbers. And we end up with negative 20 x to the 25th. Well, that's not working out either. If you continue this along, though, you would end up on term 6. And term 6 is equal to 10 choose 5 x cubed to the power of 5 negative 2 over x squared to the power of 5 is equal to negative 8064 x to the 5th. So by brute force, we would know that the 6th term has our x squared. So we've done that. But there's a simpler way of dealing with this if you understand the patterns that you see. If you take a look at term 1 and to term 2, you'll notice that it decreased by x to the power of 5, which means that that pattern should continue through term 3, 4, 5, and 6. So if we go from T1 is 30, T2 is 25, T3 then has to be 20, T4 15, T5 10, which means just by inspection, T6 has to have x to the power of 5 in it somewhere. Obviously, we don't have the exact value because there is this coefficient out front that we haven't accounted for, but we know that it has to be T6. There is even a third way of dealing with. So again, this is inspection. The third way is if you eliminate the coefficients altogether and just focus in on the variables, we know that t to the k plus 1 has to equal x to the power of 5. Again, we're just eliminating all the coefficients for now and focusing in on the variables. Well, that's just equal to what? Well, that's equal to x cubed to the 10 minus k, we don't know what k is, times 1 over x squared to the power of k. Okay, well, we can use some power rules here, and we end up with x to the power of 5 is equal to x to the 30 minus 3k times x to the negative 2k. Okay, we can combine terms again. X to the 5 is equal to x to the 30 minus 5k. Well, we have the same base, which means 5 has to be equal to 30 minus 5k, which means k has to equal, I'll write it up here, k has to equal 5. The answer is, it is in T6. So inspection gets you there, algebra gets you there, brute force gets you there, but either way you go, you should be able to come up with the solution using any method you feel good with.